Problem number 16. Two soap bubbles of radii are 1 equals 1 centimeter and are 2 equals 2 centimeters conjoined together in the air, such that a narrow bridge forms between them. Assuming the system starts in equilibrium, the bubbles are extremely thin, and that air can flow freely between the bubbles through the bridge. Describe the evolution and final state of the bubbles. Solution to problem 16. The larger the radius of curvature of a bubble, the lower the pressure inside it. So the pressure inside the smaller bubble is greater than the pressure inside the larger one. As a result, air will flow from the smaller bubble to the larger one. The smaller bubble will shrink and eventually collapse, while the larger bubble will grow. That was the answer A, and that was the solution to problem 16. Problem 17. A particle of mass m moves in the xy plane with potential energy, u as function xy equal negative kx square plus y square over 2, the closest point to the origin x equals 0 and y equals 0 during its motion was at a distance d, and the particle's speed at that point was v naught equals 0. Which of the following statements is true regarding the path of the particle, after a long time t much greater than d over v? Solution to problem 17. Unlike the spring potential, here we have a minus sign in the potential expression. The corresponding force is directed radially outward, with a magnitude proportional to the distance from the origin. Under the action of such a force, the particles will be pushed to infinity. Note that the force does not provide a torque about the origin. Conservation of angular momentum means that the angular momentum of the particles will be the same as at time 0, that is, the tangential component of the velocity will be inversely proportional to the distance from the origin and will tend to 0 at infinity, while the radial component of the velocity will increase as the particle moves away. This means that the direction of the particle's velocity will asymptotically approach a straight line from the center. Of all the answer options, this corresponds only to answer B. For an exact solution, let the initial position of the particle be d0, and the velocity 0v. The equations of motion can be written as follows. Here omega squared is equal to k divided by m. These equations give us the following solutions. Substituting the initial conditions, we have a plus b equals d, c plus d equals 0. Next, omega a minus omega b equals 0. Omega c minus omega d equals v. Solving this system, we have a equals b equals d divided by 2. C equals minus d equals v divided by 2 omega. Thus, we obtain the following solution. In the long run, the positive exponential term will dominate, and the particle's trajectory will be asymptotic to a line passing through the origin with slope v divided by d omega. Note that the positive exponential term cannot be equal to 0, since the particle had a point of closest approach to the origin. This is the answer B, and this was the solution to problem 17. Problem 18. A particle of mass m moves in the xy plane with potential energy uxy equals kxy over 2. If the particle begins at the origin, then it is possible to displace it slightly in some direction, so that the particle subsequently oscillates periodically. What is the period of this motion? Solution to problem 18. The potential function has a saddle shape, and the direction that allows simple harmonic motion is the displacement along the line y equals x. All other directions cause the particle to deflect toward the line y equals negative x. Suppose the particle is displaced a distance L along this line. Then x equals y equals L divided by the square root of 2. Therefore, the potential energy is ca L squared divided by 4. In other words, the potential energy is the same as that of a spring with stiffness ca divided by 2. So the angular frequency omega is equal to the square root of k over 2m. And the period will be 2 pi multiplied by the square root of 2m over k. This is the answer D. And that was the solution to problem 18. Problem 19. Near the ground, wind speed can be modeled as proportional to height above the ground. This is a reasonable assumption for small heights. A wind turbine converts a constant fraction of the available kinetic energy into electricity. The conditions are such that when operating at 10 meters above the ground, the turbine delivers 15 kilowatts of power. How much power would the same windmill deliver if it were operating at 20 meters above the ground? Solution to problem 19. By assumption, at 20 meters, the wind speed will be doubled. We're asked to find how the power of the turbine scales with wind speed. The energy that's available to be extracted over a small time interval is the product of the mass of air that flows past the turbine, and the mass density of the kinetic energy of the air. The mass of air scales as V, and the kinetic energy per unit mass scales as V square, so the total scales as V cube. Finally, because speed is doubled, the power B cube of 2, which is 8 times. That will be answer E. And that was solution to problem 19. Problem 20. The International Space Station orbits the Earth in a circular orbit 400 kilometers above the surface, and a full revolution takes 93 minutes. An astronaut on a spacewalk neglects safety precautions and tosses away a spanner at a speed of 1 meter per second directly towards the Earth. You may assume that the Earth is a sphere of uniform density. At which of the following 5 times will the spanner be closest to the astronaut? Solution to problem 20. The spanner will, of course, also orbit the Earth, in a slightly different orbit from that of the ISS. The total energy of the spanner is increased by this tossing maneuver, so its orbital period will be very slightly longer than that of the ISS. After exactly 1 orbital period of the ISS, the spanner will be very slightly behind the ISS on its trajectory. At other points along the orbit, the spanner and the astronaut will be farther apart. Because the spanner was tossed inward, its initial angular velocity will be slightly higher than that of the astronaut, i.e. it will pull ahead in its orbit. At the point where the spanner's and the ISS's trajectories cross for the first time, approximately halfway around the orbit, the spanner's angular position will be maximally ahead of the ISS's. Over the second half of the orbit, the ISS's angular position is catching up to that of the spanner, and it very nearly catches up by the time they pass through the point where the astronaut first tossed it. Let us now estimate quantitatively the lag of the wrench after 1 revolution. The initial energy of the wrench switch in a circular orbit was according to Formula 1. Here V0, the orbital velocity of the ISS, the astronaut and the switch, r is the radius of the ISS orbit, and respectively A0 is the major axis of the station's orbit. Accordingly, Formula 2 is valid. After throwing the key of the main motion of the station, the total power of the key began to obey Formula 3, which after reduction turns into 4. For simplicity of calculation, we put V0 equal to 10,000 meters per second. Thus, the total relative increase in the major semi-axis, it will be 2 times 10 to the power -8, Formula 5. Next, using the proportion of the 6th third Kepler's law, it turns out delta T divided by T is equal to 3 times 10 to the power -8. Ultimately, we get a lag of the switch from the station equal to 1.6 meters, and time a little more than 93 minutes. This will be the answer C. And this was the solution to problem 20.